Hi everyone, in this final video I want to discuss and prove the spectral theorem for compact normal operators on a separable Hilbert space. I'll actually just prove it for self-adjoint operators and outline how to go from self-adjoint operators to normal operators, and I also will do the Fredholm alternative. If this gets too long, I'll make one last very short video. All right, so let's begin. We just need a definition. So let's say T is just a linear map just from one vector space, from a vector space to itself. Okay, so let's say lambda is an eigenvalue. And define E lambda to be the kernel of T minus lambda times the identity on X. A lot of times this is just written as T minus lambda. It's implied that it's lambda times I. So yeah, I think the book does it. So I'll just do that. All right, so pretty obviously this is going to be equal to all eigenvalues corresponding to lambda. Well, the 0 is always in the kernel, obviously. So it's basically all eigenvalues. Sorry, all eigenvectors. Not eigenvalues. All eigenvectors union 0. And the point here is very simply, we basically want a vector space that encapsulates all eigenvectors. Well, we always have to have 0 if we're going to deal with a vector space. So, all right, so let's prove the following useful result. Right. So if H is a Hilbert space and T is bounded, compact, then this is finite dimensional for any eigenvalue lambda. Of T. Right? And what's the proof? The proof is basically prove the contrapositive. Assume not. So assume we have a linearly independent sequence of stuff in the kernel of T minus lambda times the identity. All right. So remember that Graham-Schmidt says that whenever you have a sequence of linearly independent vectors in an inner product space, you can always basically convert that into an orthonormal sequence. More precisely, you can always perform an algorithm to get an orthonormal sequence where the span of your original linearly independent sequence is the span of your new orthonormal sequence. So in other words, because this is a vector space, E lambda, we can assume by Gram-Schmidt that this is orthonormal. If it's not orthonormal, to basically apply Gram-Schmidt, and we have an orthonormal sequence in E lambda. And if you're wondering, this is the same Schmidt as the Hilbert-Schmidt name. So Schmidt did a lot of work on Hilbert spaces and integral operators. Yeah, so we can assume that this is orthonormal. Okay, so right, so let's kind of do the same thing we've done at least once or twice. Pick any subsequence whatsoever. So for any subsequence Tx and k, what do we have? We have Tx and k minus Tx and m squared. Well, Tx and k is going to be lambda x and k because x and k is an E lambda. So x and k is either 0 or an eigenvector corresponding to lambda. So this is going to be, and sorry, before I say anything, I have to assume this is 0, otherwise this is false. So non-zero eigenvalues have finite dimensional eigenspaces. Yeah, and this is called, just like in linear algebra, this is called the eigenspace. Well, eigenspace corresponding to lambda. Right. All right, so this is going to be, well, just lambda x and k minus lambda x and m squared. Well, just simply apply Pythagorean's theorem. This is going to be bigger or equal to lambda squared x and k squared plus, or modulus lambda squared rather, modulus lambda squared x and m squared. Well, this is orthonormal, so it's 2 modulus lambda squared, and this is not equal to 0. Right? So this implies Tx and k obviously is not Cauchy. So there does not exist a subsequence of xn where Txn k converges. There is no convergent subsequence. All right. So that implies T not compact by definition. Right. And again, should be no confusion here, but Tx and k is lambda x and k, and Tx and m is lambda x and m, just simply because, well, this is stuff in E lambda. Right? Oops, sorry about that. I meant lambda x and m. All right, so next, we have the following probably proposition that everybody knows. Well, actually, before I do that, basically, the same proof gives you the following proposition, which we won't directly need. So I'll leave it as an exercise. If T is compact, then T is not invertible. Right. Yeah, basically the same idea. You basically prove that if T is compact, or rather if T is invertible, then you know that the inverse is bounded by the inverse mapping theorem. And so that means that's the same thing as saying T is bounded below, but if T is bounded below, then certainly, you know, take T, apply it to an orthonormal basis. There's no convergent subsequence because the norm of any two basis elements is 2. So that's basically the proof. Okay, so just kind of remind you of a linear algebra fact. Maybe you didn't do this with, I don't know, just remind you of a very simple linear algebra fact. So let's say, forget about compactness for a second. Let's say T is self-adjoint. 1, and really just T needs to be linear on some inner product space, whatever. So first of all, eigenvalues are real. And 2, you have orthogonal eigenspaces if we have 2 different eigenvalues, right? Okay, right, so let's just prove this real quick. Well, the proof of 1, there's not a whole lot. Tx is lambda x, then lambda modulus x squared is certainly Tx x, because Tx is lambda x, pull out the x. Well, it's self-adjoint, so this is x Tx. This is x lambda x. This is lambda bar x. Well, sorry, lambda bar modulus x squared. Well, by definition of an eigenvalue, so maybe to be clear here, this is an eigenvector. By definition of an eigenvalue, an eigenvector exists, and in particular, this is not 0. Right. So you just divide by modulus a norm x squared. So that gives me exactly what I want. Well, lambda bar equals lambda, and hence lambda is real. Okay, so yeah, eigenvalues have to be real. Nothing too surprising there. And for 2, if we have Tx is lambda x, so I mean, of course, this is true. Maybe this is not clear, it should be immediate, but this is true if and only if x is an E lambda. So here x could be 0, really. But yeah, this is true if and only if x is an E lambda. And let's say ty rather is lambda prime y. All right, so right, so what does this tell me? Well, this tells me that 1 second. Yeah, sorry about that. A little brain fart there. So 0 is tx, tx inner product y minus x. Well, let's do it. Just basically add and subtract the same thing here. So just bring the t over. This is going to be bring the t over for this one. It's txy minus x ty, because t is self-adjoint. So this is going to be equal to tx is lambda x. Okay. Well, ty is lambda prime y, and we know lambda prime is real, so there's no need for a complex conjugate. So this is going to be equal to lambda minus lambda prime xy inner product, but we're assuming this is not equal to 0. So that implies x is perpendicular to y. Right, and that takes care of the easy proof. All right, so I need one more fact. All right. So actually, I want a definition. So I'm going to use this notation. Sigma p of t is going to be just a collection of all eigenvalues of t. So let's say t is just a linear map on a vector space. So p here is for point, and this is often called the point spectrum. If you study functional analysis, particularly operator theory, more deeply, then you'll talk about the spectrum of a of a linear operator, but I don't really want to get into that. Bit of a distraction at this point. So it's just convenient notation for this collection of all eigenvalues. So we have the following theorem. Really a lemma, but it's worthwhile as a theorem unto itself. So again, if I have a compact self-adjoint operator, I shouldn't say again because here we're not assuming self-adjoint. If we do have a compact self-adjoint, and if H is a Hilbert space, then this is either finite or countably infinite. Right. So if the latter is true, and if we enumerate this by lambda n, then the eigenvalues have to approach 0 as n goes to infinity. Right. So let's prove this. So the way we prove this is it's actually the same proof as in basic analysis, where you prove that a monotone function on an interval can have at most countably many discontinuities. You basically write, here we're going to write the set of all eigenvalues as the countable union of finite sets. The countable union of finite sets is countable, countably infinite rather. Or I mean, it's if it's really if all of these sets are if all but finitely many of these sets are finite, then certainly the countable union is finite, because you're just eventually taking just union, just taking the empty set and with your union. But if infinitely many of these finite sets are not empty, then the countable union is certainly countable. So anyway, enough of that. Let's write stuff down. So assume this is infinite. I mean, if it's not infinite, we're done. There's nothing to prove. We're saying it's either it's either finite or countably infinite, where the limit goes to 0. So let's assume it's infinite. Okay. So I want to prove the following claim, which is AN is set of all eigenvalues with modulus bigger or equal to 1 over n. And I claim this is finite. Okay. Yeah, so let's assume otherwise. I mean, it should be clear, as I said, basically, sigma p is going to be certainly the union of all these, well, union 0. So sigma p of t, sigma p of t is a union of these ANs and possibly 0. So if we can prove that this is finite, then certainly we'll at least have that sigma pt is countably infinite. Okay, well, why is this true? Assume not. So pick, let's say, lambda k infinite in AN. So pick eigenvectors and make clear that, these are all distinct. We're picking an infinite sequence in AN where all these are distinct. Right? Obviously, if AN is infinite, we can do this. So pick eigenvectors. So the proof strategy here is kind of the same as last. The theorem we had here. It's basically the same kind of proof strategy. So pick eigenvectors, let's say xk. Or rather, pick eigenvectors. I guess I'll just write it like this. Corresponding to lambda k. So maybe I'll write it like this. It'll make a little more sense. Okay. Again, by Graham-Schmidt. Well, actually, you don't need to do Graham-Schmidt. So take any subsequence, again, xnk. Yeah, so actually, let's pick normalized eigenvectors. Obviously, you can always, I mean, if this wasn't clear, so if you have Tx is lambda x, and x is not equal to 0, then you also have T, obviously, x over the norm of x is lambda x over the norm of x. So you can always pick a normalized eigenvector corresponding to an eigenvalue lambda, because by assumption, this is not 0. Right? So we have these eigenvalues in AN. Pick normalized eigenvectors corresponding to these. Okay, so let's prove that for any subsequence, this is not going to converge, and hence T is not compact. Right? Well, not really much to this. Just like before, this is going to be lambda and k in virtue of being an eigenvector. Lambda xk, lambda nk, xnk minus lambda xnm, sorry, lambda nm. Right, but T is self-adjoint. Okay. So this is going to be equal to, by using Pythagorean's theorem, lambda nk, xnk, lambda nm, and the reason is very simple. It's not clear. Well, T is self-adjoint, and we said all these lambdas are distinct. So we know that eigenvectors corresponding to different eigenvalues are orthogonal. Right? And of course, this equals, these two are equal to 1. So this is going to be equal to lambda nk squared plus lambda nm squared modulus. Well, modulus is really not needed because these are T is self-adjoint, so the eigenvalues are real, whatever. But these are not just any eigenvalues. These are very special eigenvalues. They're an AN. So it's each eigenvalue in absolute value is bigger or equal to 1 over n. So this is 1 over n squared, 1 over n squared. So it's 2 over n squared. And maybe to emphasize, let's assume that for some fixed n0, that these that this is infinite. Right. Just want to stress that. Right. So this implies, again, Tx and k not Cauchy. That implies T not compact. That's a contradiction. We're really proving the contrapositive. If T is not compact, I mean, we're proving yeah, we're proving really contrapositive. AN is infinite, then T is not compact. Whatever. And so this has to be finite. Again, this n naught here is fixed, so we can even just say this is delta positive. So no matter what k and m are, as long as they're different, this is always going to be bigger or equal to delta. It is not going to be Cauchy. Right? And these are normalized, so each one has norm 1. So obviously it's a bounded sequence. So this violates compactness. Okay, so yeah, now we're almost done. Just a reminder of what I said. Basically, this says that sigma p of t is going to be this union. Well, if you have an eigenvalue that's not 0, then it has to be bigger or equal to 1 over n for some natural number n. If it is 0, well, maybe yeah, so I mean, if 0 is an eigenvalue, meaning the kernel is not trivial, then sigma p of t is this union. Or otherwise, if 0 is not in sigma p of t, then just for consistency, sigma p of t is this union here. So this is countably infinite. All right, so basically, if you think about it, this also proves the other part. Let's just write out the details right now. So yeah, so finally, let's say we have lambda k is sigma p of t. And again, these are all distinct. So that. Okay. Yeah, so how do we prove that lambda k? I think I had n here. That matters, but well, let's just prove this like we always prove something converges to 0. let's say epsilon is positive, and pick n bigger than 1 over n. So 1 over n is less than epsilon. We proved that each of these ANs is finite. So in particular, there exists a big N for n bigger than n, or maybe I guess I'll stick with k, maybe not the best, whatever. Let me stick with actually n, and I'll just use, like I had before, like n naught, just some, you're just fixing some integer n bigger than 1 over epsilon. Right, so this is finite. Eventually, all of these, because they're distinct, are not going to be in AN. After a certain point, after a certain point, it's not going to be in AN. And these are, we're assuming this is infinite. So lambda n is not an AN naught. Sorry, AN naught. So this implies that well, what does this mean? This means that lambda n is less than or equal to 1 over n naught is less than infinity, less than epsilon rather, if n is bigger than n. And that proves that the limit of these eigenvalues is 0. All right, so I need one more concept, and that is invariant and reducing subspaces. And particularly in operator theory involving holomorphic function spaces, there's quite a bit of research on this kind of topic. So let's say we have a closed subspace of a Hilbert space. Now let's say T is a bounded linear operator on H. So we say M is an invariant subspace of T if kind of the obvious thing is true, T doesn't, T takes big M to big M. So T doesn't, just T takes big M to big M, right? So I should say really a closed subspace. So actually taking concrete operators and figuring out what their invariant subspaces are explicitly is a really, really rich question. It's a really often deep question. That's often highly non-trivial. And in particular, for the shift on little L2, there's a really beautiful characterization of invariant subspaces of that that actually surprisingly has to do with the holomorphic Hardy space. And you might think, what on earth does the shift have to do with the holomorphic Hardy space? Well, the answer is to basically answer the question of what do the invariant subspaces look like. You basically take a isomorphic copy of the forward shift on the Hardy space, where you have all the tools of complex analysis at your disposal. But that would take another, I mean, actually doing that would probably take 4 or 5 videos. Anyway, we say M is a reducing subspace. I don't know why I have sup. T if both T M is a subset of M and Tm perpendicular orthogonal complement rather is a subset of the orthogonal complement. And I'll explain in a moment why it's called reducing and why this is quite useful. All right, so a very simple lemma. Operator theory, I think, is quite interesting. That you have kind of little, almost trivial but important lemmas, kind of juxtapositioned between very deep and difficult things to prove. So you have M is an invariant subspace. Of T, if and only if M perp is an invariant subspace of T star. So what's the proof? Let's prove, not much to this. Let's prove this direction here. So let's say little n is in the orthogonal complement. And let's say m is in big M. So we want to prove, I want to prove that Tn is, T star n rather, is an M perp. That's my goal. I need to prove that T star m perp is a subset of M perp. All right, well, we need to check that T star n applied to M is 0. Well, just bring the T over. So M is invariant subspace of T. So by definition, that means that because little m is an M, T of little m is also an M. Well, we're assuming n is in M perp. So obviously, this means it's 0. That implies exactly what we want. That T star n is an M perp. Okay, so the other direction basically uses this. It's very straightforward. M perp is invariant subspace T if and only if well, yes. So we showed that M is invariant subspace of T implies that M perp is an invariant subspace of T star. Right, so M perp is an invariant subspace of T star implies that M per perp is invariant subspace of T star star, and that takes care of it because what is T star star? Well, obviously that's going to be T, and what is M per perp? Because M is closed, this is M. Right? Okay, so let me do an example. I want to do two examples where one of the examples went. All right, so yeah, I want to do two examples. To illustrate this concept. Okay, so let's say H is a nice, simple Hilbert space L2 of 0 to 1. And let's say we have the closed subspace NE. Let's say rather E is just anything measurable, subset of 0 to 1. Let's say NE is going to be set of all F in L2. Such that F equals 0 almost everywhere on E. Okay, so you can check almost trivially that, what can you check? You can check that NE is invariant subspace for the operator MX multiplication by F. Or really any, let's say MG. Where this is an L infinity of 0 to 1. I mean, there's literally nothing to that. GF is 0 almost everywhere if F equals 0 almost everywhere. So, yeah, MG and E is a subset of N E. Right. So also you can basically check, I'll genuinely leave this for you to check. The orthogonal complement is going to be just set of all F in L2 where f equals 0 almost everywhere on 0 to 1, take away. Yeah, so you can also, I suggest checking that the orthogonal projection, not that we really need it, but as a good exercise, check that the orthogonal projection onto NE. So denote that by PNE. Is just the characteristic function of E times f of x. Right? And the orthogonal projection onto the complement is just going to be, well, just obviously take away E. Just get a better handle on these two subspaces. Yeah, and you kind of, this gives you like a trivial decomposition of any L2 function in terms of something in the orthogonal complement and something perpendicular to something in NE rather, and something in the orthogonal complement of NE. Just, take an f, characteristic function of E times f, plus characteristic function of 0 to 1, take away E times f. Right? And same idea, there's really not much to this. G times f equals 0 almost everywhere on 0 to 1, take away E, if f is 0 almost everywhere on 0 to 1, take away E. So yeah, the product is 0 almost everywhere on 0 to 1, take away E, if f is 0 almost everywhere on 0 to 1, take away E. Okay. So that means that actually this is a reducing subspace for T. Sorry, for MG. So NE All right, so let me do another interesting example. This example is in the book, basically in the book. So let's say H is the Bergman space of the disk. Right? And remember, this is just all holomorphic functions on the disk. Where the following is finite, following normalized L2 norm is finite. All right, let's say N is the set of all, or rather the vector space of all stuff in the Bergman space, where f of 0 is 0. You can check very trivially that this, well, we don't really need actually the orthogonal complement, so I won't write it down, but it's just all f where f is constant. It's just all constant, constant functions on the unit disk. Right, so let's say G is bounded and holomorphic. Right. So let's say MGF is just multiplication by G. Right. So certainly, obviously, this is an A2. If F is an A2, and this is, because G is bounded, this is obviously a bounded operator. Yeah, so certainly MGF of Z, 0 is going to be G of 0, F of 0. This is 0 if F is an N, because then F of 0 is 0. So obviously N is an invariant subspace for multiplication by G, right? Okay, so I claim that N isn't necessarily a reducing subspace of MG. Okay. Okay, so just want to remind you of the lemma we had before. I don't have my previous whiteboard slide. So remember the lemma we had, and I'm going to make this a little, change it a little bit. M invariant subspace of T is equivalent to M perp invariant subspace of T star. If T is a bounded operator on a Hilbert space and M is a closed subspace. Certainly, you can check this is a closed subspace. It's an easy homework. It's really not much to it. Convergence in A2 implies pointwise convergence. So this is pretty trivially closed subspace of A2. Right. So normally, yeah, what we had last time was, we had a moment ago was this. So let's replace T with T star. So we get M is an invariant, or rather, M perp is an invariant subspace of T is equivalent to M being invariant subspace of T star. Right? So let's put this to good use. I'm using N, same notation as the book. Yeah, so let's prove this claim here. So let's say for simplicity, or let's take probably the simplest example that works, which is G of Z is Z. Okay. So what is the adjoint of MG? Well, you might say, well, obviously it's MG bar. We've done this a million times. Well, no, not really, because MG bar certainly takes L2 to L2, but it does not take the Bergman space of the Bergman space. You have a holomorphic function f multiplied by G bar, where G is holomorphic. That's not going to be in general holomorphic. I don't think it's ever going to be holomorphic unless one of them is 0. Okay, so instead, this is going to be, and you can check this very easily. It's not trivial, but it's not too hard. It's it's multiplication by G bar followed by the orthogonal projection from L2 to the Bergman space. So this here, again, certainly L2. Particularly, this is bounded by 1 on the disk. So this is an L2, and this whole thing here now, because we're taking the projection, takes L2 to Bergman space. This is in A2. Okay. So let's say f of z is z, right? And certainly this is an n. So I guess I had m before, but you know, let's say n is a closed subspace. Whatever. Okay, so I claim that well, mg star of f is not in n. So what is this? This is going to be the projection of g bar This is the orthogonal projection of modulus z squared, and you can expand the orthogonal projection using the canonical orthonormal basis, z to the n over square root of n plus 1. And if you do that, you can check very easily, it's not trivial again, but it's not hard, that this is 1/2. Okay. So this is not an n. Okay. So mg star n is not a subset of n. So that implies, just from here, that mg n perp is not a subset of n perp. Okay. So yeah, mg is not, so n does not reduce mg. It's an invariant subspace, but it does not reduce. Okay, so very briefly, I want to kind of tell you what the point of why we call the definition of a reducing subspace a reducing subspace, and what's kind of the point. Well, the point is, let's say M be a reducing subspace of T. So in other words, let's say, well, let's just write that. Say M is a reducing subspace of T. Okay. Right, so then for any x whatsoever, well, write x as x1 plus x2, where x1 is in M and x2 is in M perp. Right? So if T is a reducing subspace, we know that Tm is a subset of M. So this is an M. And we know that Tm perp is a subset of M perp. So this is an M perp. So the idea is that T is reduced to, or rather the study of T is reduced to the study of these two maps, T restricted to M takes M to M, and T restricted to M perp takes M perp to M perp. Right. Neater. Yeah, so that's the idea. That's the idea. The study of T is reduced basically to the study of T takes M to T restricted to M takes M to M, and T restricted to M perp takes M perp to M perp. All right. Okay, so let's finally get to the spectral theorem, or really diagonalization. So remember from linear algebra, if we have a normal matrix, I guess I'll still use T, doesn't matter. So if T is a normal n by n matrix, and remember what normal means. It means T star T is T T star. For star here is just the adjoint matrix. Transpose, complex conjugate, everything. Then T is diagonalizable. And remember what that means. That means there exists unitary U, n by n unitary matrix U. And remember what that means. That means, well, we went through this before, just to remind you. U star is U star U is the n by n identity matrix. Right. So there's this unitary matrix where UM, U inverse, or U star, same thing, is D, and D is a diagonal matrix, meaning with possible repeats, it's just zeros everywhere except on diagonal. Just from this, just like in linear algebra, you can check that the lambdas have to be eigenvalues, and the columns of U have to be or have to be an orthonormal basis of eigenvectors. Okay. Okay. Right. So you probably proved this in linear algebra. If you didn't, then this is a good homework. This is equivalent, and maybe it's more, in some contexts, it's more useful. And a lot of obviously applied math, you just need to work with matrices. You don't really necessarily want to work in an abstract orthonormal basis. You just need facts about matrices. But sometimes you don't. So equivalently, there exists an orthonormal basis, K, Cn, where each one of these is an eigenvector. And scalars lambda n, where Tx can be written as a diagonal operator with respect to this orthonormal basis, meaning, well, it's basically your orthonormal basis expansion, except multiplied by these scalars. Right. And you can actually check that really this is just going to be, these are just going to be the columns of my unitary matrix here, really. You can just check that. So You can, I mean, these EKs are going to be very explicit, but right. All right, so we have the following theorem. And that is, let's say we have H is a separable Hilbert space. Sorry about that. Yeah, so let's say H is separable Hilbert space, and let's say T is normal and compact. All right. So there exists either a finite or countably infinite. Oops, not mean to do that. And I should say here, these are eigenvalues of T. It's pretty obvious. And yeah, also, all these are eigenvalues of T. Okay, so there exists, yeah, so there exists finite or countably infinite orthonormal basis ENK, or EK rather, eigenvectors with corresponding eigenvalues that lambda k, where same thing is true, Tx is going to be, and I'll just leave this as sum n because n can be finite, or n could, you know, this could be a finite sum, it could be an infinite sum. Well, okay. So let me actually just leave this alone for a moment. So I don't want to say anything just yet. So the last part of this is if lambda n infinite then this limit here is 0. Okay, so let's just look at what T, so it's pretty trivial that if this is true, then T is diagonal with respect to this orthonormal basis. Why? Let's say we have some x in my Hilbert space, and you just write x as this orthonormal basis. So it's x, ek, ek. So that Tx is going to be, T is bounded, so it's continuous. So it's x, ek, t, ek. But ek is an eigenvector with respect, is an eigenvector with corresponding eigenvalue lambda k. So this is going to be x, ek, lambda lambda k ek. Well, we usually just stick this out in front. Just looks a lot neater. So this is really just lambda k x ek ek. Right. So right. So this is what we need to prove. We need to prove that there exists a orthonormal basis for my Hilbert space of eigenvectors with corresponding eigenvalues lambda k. And we want to show that this is true. I mean, actually, we did prove that a diagonal operator is compact if and only if the diagonal goes to 0. So if we do get this, then if we do get a countably infinite number of eigenvalues, then this has to be true. Otherwise, T is not compact. But anyway. All right, so let's prove this, and the proof really isn't so bad. Right. Okay, so what's the proof? Well, the proof is, so as I mentioned, I'm going to assume, I'm just going to prove this carefully for T self-adjoint, and then I'm going to outline the proof when T is normal. Right. There's a little bit of technicality when T is normal that's not seen when T is self-adjoint, but essentially they're basically the same proof. Okay. Well, let's start off with something trivial. Let's assume T is not 0. So the norm of T is not 0, right? So I should say the proof is going to combine basically everything we've done really in this video and in the last video. Okay, so from, I believe, the last video, T is a compact self-adjoint. So we know that we have at least one eigenvalue, the norm plus or minus the norm of T. So that's our starting point. So pick, use the book's notation. So pick eigenvector, or rather pick corresponding eigenvector, let's say G1, let's say it's normalized. As we said before, you can always trivially normalize an eigenvector. Right. Okay, so yeah, so let's say M1 is the span of G1, right? Okay, so clearly M1 is a invariant subspace of T, because, well, there's not much to that. This is just alpha T G1. TG1 is lambda G1. This is going to be alpha lambda G1. That's in M1. So what does that mean? That means M1 is an invariant subspace for T, but T is self-adjoint. So let's just go back here a second. So if T is self-adjoint, then we do have, well, T star is T. So N is an invariant subspace of T if and only if N perp is an invariant subspace of T. So that means basically if you have a self-adjoint operator, then the concept of invariant subspace and a reducing subspace is the same, right? And that doesn't violate this example. Certainly, this is not self-adjoint, obviously. So this in particular implies that that M1 perp is an invariant subspace of T, right? All right, so basically we're going to say T1 is T, and let's say T2 is T restricted to M1 perp, right? Okay, so it's basically trivial that if you have a compact operator and you restrict it to a subspace, then that's also compact. I mean, it's literally just by definition. Nothing really to that. And and also if you have a self-adjoint operator and you restrict that to a subspace, closed subspace, then that's also going to be self-adjoint. So this is compact self-adjoint. So we can repeat, basically,